Okay, for this method, what happens if we have a function that looks like this and we try our fair limit theorem? We want to see if the function is continuous at 0. So I plug in 0 to the function. That gives me the square root of 1 is 1. So it's indeterminate. That means the function is not continuous at this target value 0. But the 0 in the numerator here tells us that this 0 up here tells us that we can do some algebra to make it an agreeable function, a function that's just like it, that's continuous. And then we can find the limit of that function. So the method we use is called rationalizing the numerator. So if you remember from geometry, you were rationalizing the denominator of some values. Like if you had a number like this, we didn't want the square root in the denominator. We said that we're going to rationalize the numerator by multiplying both the top and bottom by that square root. And that would be called, you were just calling it rationalizing. But now we're going to say rationalize the denominator because in calculus you're going to want to rationalize the numerator. And so that means there's a square root in it making the numerator irrational. And we want to rationalize. So the way you do that is you multiply both the top and the bottom by the conjugate pair of that numerator. You can't just multiply by the same square root because it's two terms. If I go back to that geometry example, if I had something like this in the denominator, multiplying by a square root of 3 wouldn't work. You'd have to multiply by the square root of 3 minus 5. Okay, and I'm not going to go through how to do that, but just trust me that in the denominator, there would no longer be a square root. It would be 3 minus 25. That's what your denominator would turn out to be. And there would no longer be a square root in it. So that's why it's called rationalizing. You're getting the irrational out of there. So in this one, sorry, I wanted to point this out. This is the conjugate pair that we multiply by up top. Notice the sign, everything's the same, but the sign is different. It's mostly about the sign. That's what makes it a conjugate pair. So as we do that multiplication, we're going to do the square root of x plus 1 times the square root of x plus 1. And that would give us x plus 1. Then when we do the square root of x plus 1 times the 1, we'll get a positive of that number. And then when I multiply the negative 1 times the square root of x plus 1, we'll get a negative version of that number. Therefore, they will equal 0 when I combine them, so they will not show up in the numerator. Then I have to do the negative 1 times the positive 1, and I get negative 1. So that's what you get when you multiply the numerators. And the denominator, we're not going to actually multiply it out. We're just going to keep track that that's what we would do. So we're going to just write x times this quantity. So that's what I have here. Now I'm going to simplify the numerator. And because I didn't multiply out the denominator on that last step, I can divide the x into the x. And I end up getting this is now an agreeable function. It's just like our other function, except at the target value, it is no longer indeterminate or not continuous. The limit's indeterminate. The function is now continuous at that target value. That's called an agreeable function. So to find the limit, since it's continuous, I can just go find f of 0, and that will be the same thing. So now if I plug in 0, I get 1/2. So then that's going to be the limit as x approaches 0 of this function, which is also then going to be the limit of this function. What did we have? The original function, x plus 1, right, minus 1 over x. Yeah. All those things are equal, so that's the answer. We're going to talk about in class how we connect. Why is that also the answer of that original limit? Thank you.